Hello, welcome to my talk on broadband interstellar communications. My name is Dave Messerschmidt. I'm a emeritus professor of electrical engineering and computer science at the University of California at Berkeley, and I've spent a good deal of the past decades specializing in electronic communications, and recently have been looking at the challenges of communicating information from one interstellar system to another. So we're going to be talking about information-bearing signals, not signals which are simply trying to attract attention. We like to abstract a communication to what we call a channel, which in this figure is the relationship between a baseband signal, which carries a digitally modulated waveform, to a baseband channel at the receiver. Now obviously there will be modulation up to passband at some frequency that's friendly to communication through the atmosphere and through the interstellar medium, and then demodulated back to baseband at the other end, but we're omitting those modulation-demodulation steps. We are assuming that the signal is band limited to B, which is the bandwidth, by bandpass or low-pass filter at both the receiver and at the transmitter. This is not a characteristic of the electromagnetic propagation between stars, but rather is an artificial restriction of bandwidth, presumably to check on to constrain the amount of noise that interferes with the signal. So what we're interested in this talk is specifically the relationship between the design choice of bandwidth B and the other parameters of the communication, such as the transmitted power and the reliability and the other characteristics. So the signal, which is bandpass limited and modulated up to a carrier signal, passes through the interstellar medium, or ISM, where it's subject to certain impairments that we're going to discuss a little bit later. And at the receiver, there is also going to be sky noise, a major portion of which is the so-called cosmic microwave background, or CMB. That's noise that's left over from the Big Bang, which impinges upon the receive antenna and is a fundamental limitation to our ability to communicate. There's also radio frequency interference, or RFI, likely in the vicinity of the receiver due to other radioactivity at similar frequencies that are incidental to this interstellar communication. In terms of the resources required for this communication, first of all, we're going to assume that the bit rate, or the bits per second, is R. And there are two major resources of interest. One is the average energy per bit, epsilon. The average power is equal to the average energy per bit times the bit rate. And so the average energy per bit is an important parameter in terms of the size of the transmitter, the capabilities of the transmitter, and also the cost of energy for transmitting the signal. Another parameter of great interest is the bandwidth B, but we're actually going to deal with a normalized version of B called the bandwidth expansion, which is the ratio of the bandwidth to the bit rate. So for example, if the bit rate is 1 bit per second, as might be typical, nice even number for an interstellar communication context, and if the bandwidth is 1 megahertz for the signal carrying that 1 bit per second, then the bandwidth expansion factor is 1,000,000. The average power scales in direct proportion to the bits per second if the other parameters are constant, and the bandwidth required scales with the bit rate if the other parameters are constant. Now, an interstellar communication is quite a bit different from terrestrial and near space communication in its characteristics of bandwidth and energy, and the relative importance of bandwidth and energy. As we'll see in a moment, there's a fundamental trade-off between bandwidth expansion and energy. The larger the bandwidth expansion that we're willing to use, the lower the energy per bit that is allowable at a given level of reliability. On Earth or in terrestrial applications, generally we're very interested and very motivated to minimize the bandwidth required for transmission. The reason for this is that the government divides up the spectrum to different uses, and a given amount of bandwidth becomes very valuable commodity, which therefore we'd like to minimize its use and minimize the bandwidth. On the other hand, the energy, which is related to the radiated energy from the transmit antenna, is generally not a particularly important quantity in terrestrial communications, because the radiated energy is typically pretty small, and in particular much smaller than the energy required to operate transmitter and receiver, the electronics. So on Earth we're usually interested in minimizing bandwidth and not so concerned with minimizing the energy per bit. But I would contend that in interstellar applications the opposite is true. First of all, as I've shown above, there's no apparent penalty for using a larger bandwidth expansion. The reason being that the interstellar medium itself does not in any way particularly constrain the bandwidth, within reasonable bounds. And there's no competing use for that same spectrum. On the other hand, there are major benefits in the interstellar case for smaller energy per bit. The reason being that the energies required are generally very large because we're communicating such a large distance. And there's the 1 over distance squared loss of energy as the signal propagates. If we are able to reduce the energy per bit, then for a given average power budget, there are several good things that we can accomplish. One is we can transmit at larger bit rates, or we can transmit at greater distances, or we can transmit to more simultaneous targets. Sorry about that. There are only benefits that accrue to using a smaller energy per bit. Now, a small energy per bit plus the characteristics of the interstellar medium, as we'll see later, together dictate pretty specific signal characteristics that we would like to see. That is, communicating at low energy per bit through the particular impairments introduced by the ISM says a lot about the kind of signal that we're going to use. It may also be that signal discovery is easier, as we'll see later on. That's not obvious now. And also there is greater differentiation from RFI. The reason for that is that since the objectives are so much different from terrestrial communications, the kinds of signals we use turn out to be quite different, and that makes them look more distinctive from radio frequency interference. So it turns out that communications is subject to fundamental limits, as established by Claude Shannon back in 1948. And those fundamental limits are very useful because they tell us what we can shoot for, what is possible. In particular, Shannon in 1948 showed that for a very general class of channels, which includes this interstellar communication, that there's a threshold in energy. So at a given bandwidth or given bandwidth expansion, there's a threshold in energy. And if the energy per bit is above that threshold, then communication with arbitrarily good reliability becomes feasible. Reliability is usually measured by the error rate, the rate at which the bits are communicated incorrectly. On the other hand, below that threshold, high reliability is not possible. Now, there were a couple of very surprising observations coming out of that, surprising to the communication specialists at the time. One was that reliability is not possible below a certain energy per bit. It was sort of always assumed that if you put in more work and use more sophisticated techniques, that you could always get a better result. But the Shannon results say that's not the case. As soon as you approach the fundamental limit or threshold on energy per bit, it's not possible to go any lower without sacrificing reliability. The other was the observation that you can get arbitrarily good reliability because the specialists at the time sort of thought that noise always causes errors, and therefore you always have to live with errors. And there would be no way that you could get an arbitrarily high reliability, but in fact, Shannon showed that that was the case. So the question for us here is the relationship of this error rate, this fundamental bound on energy, to the bandwidth or the bandwidth expansion ratio. Now, the first observation is that if we increase the bandwidth to a higher level, then so we go up to this higher level of bandwidth, then we can do just as well as we can with the lower bandwidth. The reason being that obviously we cannot use that extra bandwidth, and any technique that's available at the lower bandwidth is available at the higher bandwidth, and therefore we can do just as well. However, if we actually use that extra bandwidth, then there's a good possibility that we might be able to lower this threshold on the energy per bit that it's allowable. And in fact, that's generally the case. Using higher bandwidth will result in a reduction in the threshold on energy. We can communicate with lower energy per bit with higher bandwidth. However, it's obvious that in order to do that, we must actually use the extra bandwidth, because otherwise we're operating back in the regime of the lower bandwidth. So we get a characteristic of energy per bit versus the bandwidth expansion, a curve like this, which divides the regime of reliable communication from the regime of unreliable communication. And this curve is convex, such as we've shown here, as this general characteristic. As the bandwidth expansion increases, the energy per bit at which we can achieve reliable communication decreases. And that's a good thing. So greater bandwidth is good. So let's look at the exact characteristics for the interstellar medium. And first of all, let's get rid of the RFI and the ISM, which are fairly complicated phenomenon, and concentrate on the additive noise due to the cosmic microwave background, which is, at the end of the day, it turns out the fundamental limitation on on our communication between stars. Not too surprisingly. On this talk, we're going to consistently ignore RFI and focus on the ISM and the cosmic background radiation. For now, I'm going to ignore the ISM and look at just the cosmic background. We're going to assume that the cosmic background radiation has a power density spectrum which is constant with frequency. So it's a flat noise and Gaussian noise. And this is the energy density, meaning the energy per hertz of bandwidth, watts per hertz. It turns out then that this curve for that particular simple channel has an asymptote. It doesn't go to zero energy as the bandwidth increases, but it goes to some finite energy. And that finite energy asymptote is the power spectral density times the natural logarithm of 2, which is about 0.69. Okay, so this gives us a global minimum energy which cannot be violated. That is, communication due to the cosmic microwave background radiation, the energy per bit cannot be lower than n0 log 2, where n0 is the Boltzmann's constant times the absolute temperature at the system temperature at the receiver. Let's give an example. For the cosmic microwave background, the minimum temperature of the noise in the receiver, due to only the CMB, is about 4 degrees Kelvin, a little less than 4 degrees Kelvin. If you plug in that formula, you find that the energy per bit is a very small number when measured in something units like joules, but a convenient unit is the number of photons that are required per bit, which is at 5 gigahertz. Might be a fairly typical frequency for communication. At 5 gigahertz, the energy per bit is about 8 photons, which is not very many photons that have to be delivered to the receiver. Now, of course, this, in terms of the average transmitted power, will be influenced by the size of the antennas, the collection area of the receive antenna, and some other factors, and you can always work backwards to figure out what the transmitted power would be. So let's look at another specific example in terms of concrete antennas and a concrete distance. So if we assume that the absolute minimum energy delivered to the receiver is 8 photons at 5 gigahertz, we assume 1,000 light years distance, so we get a 1 over r squared loss, 1 over distance squared loss, where distance is 1,000 light years. Might be a typical figure for another stellar system that harbors an intelligent civilization, if those exist out there. And assume at the transmitter and receiver that we have 300 meter diameter antennas, which would be comparable to the Arecibo antenna that we have here for radio astronomy on Earth. Then it turns out that the transmit energy per bit has to be about a half of a watt hour. Now it's kind of interesting to raise the question of what would that cost if we were to transmit information to a star that was 100 light years away using 300 meter antenna, and we assumed that they had a 300 meter antenna as well. Then that costs about $368 per megabyte at 10 cents per kilowatt hour, which would be a fairly typical figure for the cost of energy here on Earth. Now in practice, this is the absolute minimum that can be achieved. In practice, we would expect that perhaps the reality will be an order of magnitude or 2 orders of magnitude more energy than this, which would raise the cost to about $3,000 or $30,000 per megabyte. If we're transmitting a lot of megabytes of information, we're transmitting that information over and over again because we don't know when the party at the other end is listening. And if we transmit to multiple destinations, multiple stars out there at 100 light years, then of course the cost is multiplied accordingly and can get pretty expensive. So the fairly high expense of this energy is a motivation then for reducing the energy that we're using in our transmission. Well, this shows the this curve of energy per bandwidth expansion for the particular case of cosmic background radiation. And what we're measuring on the vertical axis is actually the ratio of energy per bit to the power spectral density of the noise. The power spectral density has units of energy, and so this is a unitless quantity. Okay, on the horizontal axis, this quantity is the bandwidth expansion, the ratio of bandwidth to bit rate. And we get a curve sort of qualitatively like what I showed earlier. It has a non-zero asymptote out here, which is equal to log of 2, or 0.69. We're showing this on a log-log scale, so there's about 7 orders of magnitude represented here in both the energy dimension and the bandwidth dimension. So it's a large range. The curve is similar to what I showed earlier, but this is the specific curve that applies. Now, typically in terrestrial systems, we're trying to operate up near this boundary at low bandwidth, which means that we're sacrificing energy. For example, a typical cellular telephone system on Earth will try to operate up here at about 5% bandwidth expansion. That is, the bandwidth is about 5% of the bit rate, which means that there's the energy per bit is about 5 orders of magnitude larger than this minimum. And I've argued earlier that for interstellar communication, we want to operate at higher bandwidths. One of the reasons for that is we'd like to get a smaller energy per bit, which means we want to be near this lower boundary, lower energy per bit, and we don't care so much about bandwidth. Another big reason, which I'm going to elaborate on later, is the simplicity argument, and that is that since we don't have coordination between transmitter and receiver, we have to use techniques that are very simple and easy to reverse engineer at the receiver, and easy to discover at the receiver. And it turns out that getting near this boundary is very hard in general. It actually took about 5 decades of research to arrive anywhere near this boundary over here at the low bandwidth level. But it turns out that it's pretty simple to get near this boundary up at very high bandwidths. And that's because we're essentially eliminating one constraint from the design problem. So that argues in favor of using large bandwidth expansion ratios. Now let's ask what happens when we add in the interstellar medium to this situation. What is the effect of that? Well, it's a pretty complicated situation with the interstellar medium, but it can be boiled down to about four major impairments introduced in propagation through the interstellar medium. And these impairments divide themselves up into propagation impairments and motion impairments. In terms of propagation impairments, these are caused by clouds of ionized hydrogen gas that occupy the interstellar medium. Left over, this hydrogen gas, which is used in star creation, but it's just floating out there, and it's quite turbulent. And there isn't much of it. It's very low density, very low temperature, but at very long distances of propagation, its effects become significant. And one of the effects is so-called plasma dispersion, and another effect is scattering. The dispersion is due to the absorption and re-emission of photons by free-floating electrons, which turn the interstellar medium into a conductive medium, and scattering is caused by inhomogeneity in those clouds of gas. But if the bandwidth of the signal is below some threshold here, it turns out that those effects can be ignored, and effectively it's as if the interstellar medium didn't exist from the point of view of these propagation effects. There's also motion effects due to the motion of the transmitter and receiver. Acceleration causes Doppler shifts, and there's a phenomenon called scintillation due to the motion of the receiver through this scattering field. And it's a little bit like Rayleigh scattering in terrestrial communications, if you're familiar with that. But these effects limit the time coherence of the signal. That is, if a signal is below a certain time duration, then those effects are small enough to be ignored. So together these create what I call an interstellar coherence hole, or ICH, which means that if the bandwidth of the signal is less than a certain amount and the time duration of the signal is less than a certain amount, then basically the interstellar medium is transparent to that signal, except, of course, for attenuation due to propagation losses. Now we can make use of this to create a communication signal by basically composing the signal of waveforms which satisfy the bandwidth and time constraint. And such a signal would look something like this. Each one of these squares represents a signal which is short enough in time duration that it is not affected by the motion effects, and it's narrow enough in bandwidth that it's not affected by the propagation effects. So it essentially whomps right on through the interstellar medium without any noticeable impairment. And now we can do a superposition or a summing of signals of that type and make use of the linearity of the medium to say that a more complicated signal structure can be communicated through the ISM by a combination of these coherence hole waveforms. So, for example, at this first time we have a set of waveforms which are different carrier frequencies so that they don't overlap each other in frequency, but each one is narrow enough that it doesn't violate the bandwidth constraints, and the duration is short enough that it doesn't violate the time constraint. And now we can modulate each of these waveforms at different frequencies and at different times by phase and amplitude and build up a more complex signal. Now this type of signal that I've shown here is actually what we do on Earth in today's modern wireless communication systems, such as the mobile cellular system and the Wi-Fi system that you use in your to connect your computer to the network. Both of these, and in fact I would say can safely say that any wireless radio system that's designed today would utilize a signal with a structure with a lot more complexity and bells and whistles added to it, but with this basic structure for exactly the same reason that we're using it here. And this comes under the name of orthogonal frequency division multiplexing, or OFDM. So it wasn't always the case, but today there's a consensus that this is the best structure to use for a signal for earthbound wireless communication systems. And so that gives additional validation for the merits of this approach. Now, what I have shown about 5 years ago was that a signal with this structure passed through that ISM can approach the fundamental limit on energy per bit, lower bound on energy per bit, as we allow the bandwidth of the signal to increase without bound. So this says that the ISM does not affect the lower bound on energy per bit through the ISM. It does affect the energy per bit at finite bandwidths, especially at low bandwidths. But if we allow the bandwidth to get large, then it doesn't affect the energy per bit that is achievable. And in particular, that minimum energy per bit can be achieved asymptotically at high bandwidths by using a very simple form of this signal, which I call location coding. So let's approach the fundamental limit with a practical signal that works for the interstellar communication application. So to see where this comes from and to motivate this, let's first of all observe that we want to use a technique in the interstellar medium which is very, very simple. And what could be simpler than the very first digital electronic communication technique out there, which was dates to 1837, which is Morse code. Morse code used the idea of dots and dashes to communicate letters. Da, 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 that sort of signal. The operative feature of this Morse code that's important to our present discussion is that each one of these dots and dashes is just a simple packet of energy, if you can think of it, a bundle of energy. There's no amplitude or phase modulation. It's just, is the bundle of energy larger or smaller, and that's the indication of whether we're communicating one bit of information, a 0 or a 1. Now, that was what was invented back in 1837 when there was no electronics. Literally, there was no electronics. So this was simple enough to work without any electronics. So 100 years later or so, when we had the electronics and we came back to the idea of communicating digitally, we took this basic idea and added another wrinkle to it, which was to add phase and magnitude modulation to this simple bundle of energy. Think of it as a piece of a sinusoid, a short piece of a sinusoid or carrier signal, and we added phase or magnitude modulation. The reason we went in that direction was magnitude modulation or bandwidth conserving, because if we communicate information through multiple phases or multiple magnitudes, that has no effect on the bandwidth. So we're communicating extra information without consuming any additional bandwidth. But we're paying obviously a price for that, as we know from the fundamental limit I showed you earlier. Whenever we conserve bandwidth, we must be paying a price in energy per bit. And in this case, the reason we're paying a price is because the phase and magnitude modulation reduces the noise immunity of the signal. Signal becomes more susceptible to noise. So what we'd like to do in the interstellar medium, as distinct from terrestrial communications, is to be energy conserving and not worry so much about bandwidth. In fact, perhaps not worry about bandwidth hardly at all. And so we can use a technique which I call location coding. And it was observed that this simple technique I'm about to show you, it was observed back in about 1960 that this technique, or a larger class of techniques like it called orthogonal coding, could achieve the minimum energy asymptotically as the bandwidth grows to infinity. So the way this location coding works is by locating a single bundle of energy within a grid of possible locations. And now we communicate the information by the grid that it's located in. So associated with each one of these frequency time coordinates within this grid of times and frequencies, associated with each bin in this frequency time coordinate system is a certain set of bits that are being communicated. And by locating where the energy lies, we can communicate that information. So there's no amplitude or phase modulation. We're communicating information by the location in time and frequency of the energy. So if we have k times and m frequencies, then there are k times m locations, and therefore there's logarithm 2 km bits of information communicated by the location of one of these bundles of energy. But the key point is that we're communicating this much information with only one bundle of energy. So as we increase k and we increase m, we're not increasing the number of energy bundles that are required, but we are increasing the number of bits of information that is communicated. So it's a little bit like the amplitude and phase modulation is free in terms of bandwidth. This technique is free in terms of energy, but does increase the bandwidth, because as we increase m in particular, then the bandwidth of the signal has to increase. So a signal of this type, this so-called location coding type, might look like the following. Each one of these dots represents a bundle of energy in time on the horizontal axis and frequency on the vertical axis. And each one of these dotted outlines contains 2 to the 11th possible locations for this bundle of energy, meaning that it communicates 11 bits of information. And only one of these locations is occupied by energy, so that specifies those 11 bits. So we have a sequence of these squares, each one having a bundle of energy in a different location in general. And over time then we're communicating a stream of bits. Now it's useful to give you a numerical example, see how this works. First of all, let's assume that we communicate with 2 to the n locations in time and 2 to the m locations in frequency, which means that we have the time specifies one of n bits and the frequency specifies one of m bits, and then the total time required for this one block representing m plus n bits is of length t0 times 2 to the n, where t0 is the time of one of those interstellar coherence holes. So T0 is a characteristic of the interstellar medium, and you can think of it as being essentially fixed. As we change n and m, T0 remains fixed because it's a property of the propagation through the interstellar medium. And likewise, the bandwidth is B0, where B0 is the bandwidth of one of those coherence holes times 2 to the m. So again, B0 is a characteristic of the interstellar medium, which stays fixed as we change n and m. Then the bit rate is equal to the number of bits that we're communicating divided by the time that it takes to communicate those bits, T0 times 2 to the n. And from that we can solve for m in terms of n. So what happens is, as I increase n, the number of bits that I'm communicating this way, so this whole block gets longer. As we increase n, then m increases. In fact, it increases exponentially due to this 2 to the n term. M increases, and therefore the total bandwidth of the signal increases. And we're representing more and more bits with a single bundle of energy, so therefore the energy per bit is tending to decrease. So as we increase n, the number of bits coded in the time, the energy per bit tends to decrease and the bandwidth increases for constant bit rate, constant coherence bandwidth, and constant coherence time. So here's a concrete example. Suppose that we want to transmit 1 bit per second. Then the ISM, let's say, tells us that the coherence time is 1 second. That's actually not too far from reality on most situations. These parameters T0 and B0 depend upon the path, depend on the direction that we're communicating and the particular conditions of the ISM in that direction, and they also depend on the distance that we're communicating. So these T0 and B0 will be somewhat different if we're communicating to different stars, generally not dramatically different, but somewhat different. And let's suppose that T0 is 1 second and B0 is chosen to be 1 hertz. Now, generally, the B0 of the ISM is on the order of kilohertz for most situations, but we're going to choose it to be the absolute minimum that we can get away with, because a signal with time duration 1 second can't have a bandwidth less than about 1 hertz. So this is about the lowest bandwidth we can get away with. And so if we choose, for example, n equal to 4 bits in the time dimension, then m, according to this formula, has to be 12 bits. And the bandwidth then is equal to 1 hertz times 2 to the 12th, or about 4 kilohertz. So we're talking about 1 bit per second, 4 kilohertz bandwidth, and so the bandwidth expansion factor is about 4,000 for this example. Now if we were to, and that by the way is still not a very large bandwidth, that's still at audio frequencies on the order of the bandwidth of a telephone channel here on Earth. If we want to get greater energy efficiency, then we should increase n here, 5 bits, 6 bits, and so forth. As we do that, m will increase exponentially, get larger and larger, and the bandwidth will increase exponentially, and at the same time we'll get better, lower energy per bit. So in terms of the reliability of this scheme that I've designed, this location coding scheme that I've described, it's very easy to detect this signal. Basically, you look at all the feasible locations and you choose the one with the largest energy in it, and that becomes then can be decoded into the bits of information. Now, of course, the lack of reliability is due to the possibility of false alarms. There may be, just due to noise alone, larger energy in one of these other bins than in the actual bin, which we call a false alarm event. And as the bandwidth of the signal increases, the number of possibilities for these false alarm events grows, and to compensate for that, we have to increase the energy of the signal, the energy here. So the energy doesn't stay constant as we increase the bandwidth. The energy does have to increase. However, the energy increases more slowly than the bandwidth. And it turns out that the increase in energy is in fact not very large. On the order of a factor of 2 or something like that, as we increase the bandwidth. So then if we plot a curve of the fixed reliability for that scheme, taking into account the probability of false alarms, the number of locations where we can get false alarms, and so on, we get a curve like this in terms of energy per bit, as opposed to plotted against the bandwidth expansion, again on a log scale, on the bandwidth expansion on a linear scale in the energy per bit. Actually, it's a log scale in the energy per bit, but it's not a very wide range of energies per bit. And it turns out then, and this is at a fixed reliability, meaning a fixed error rate, which I believe is 1 part in 10 to the 5th error rate. And what we find is that the energy per bit approaches an asymptote, which is actually a factor of 2 larger than the fundamental limit that we showed earlier. This factor of 2 is due to the fact that we're using an incoherent detection scheme. We're detecting just energy. But it also turns out that by making the scheme a little bit more complicated using a technique called time diversity, we can eliminate this factor of 2 and get a scheme that actually approaches the fundamental limit. And this observation was made back in 1960, that a technique like this could asymptotically approach the fundamental limit. And this was the first example of a concrete scheme that was discovered that could in fact approach the fundamental limit. Now the question is, if we used a signal like that, let me point out first of all that this kind of signal is you would argue is dictated by two things. First of all, the characteristic of the signal is dictated by the ISM and the fact that it has this coherence time and this coherence bandwidth. And if we were to violate the coherence time and the coherence bandwidth, we could probably still communicate. However, we would suffer a penalty in energy. We would have to communicate with a larger amount of energy per bit. So the objective of minimizing the energy leads us to the conclusion that we should use a signal of this type, which is the so-called OFDM, orthogonal frequency division multiplexing. The second observation is that the use of this location coding, where we have this sort of sparse location of energy within a grid, and we're communicating by location rather than phase or amplitude, is also dictated by the desire to achieve low energy. So in that sense, the characteristics of this location coding signal in terms of communicating location and in terms of the size of these bundles of energy in time and frequency are a result of the combination of the desire to minimize the energy per bit that we're using for communicating with multiple benefits, as we described earlier, together with the particular characteristics of the... Okay, so if this is the kind of signal that we were going to use, the question might be, how would the receiver discover such signals, not knowing where that it exists and where it exists? And this is the problem of SETI, or Search for Extraterrestrial Intelligence. We might hypothesize that this would be a very logical kind of signal to use for a transmitter out there that was trying to communicate information to us. But assuming that they were doing that, how would we discover that signal in the first place? Well, the first observation I would make is that the signal is sparse in time and frequency. That is, we expect little bundles of energy coming up at different times and different frequencies. And most times there's no energy, and at most frequencies there's no energy. But the instances of energy in the signal are isolated in both time and frequency. In order to make this reliable communication, the individual bundles of energy have to actually be more energetic to deal with this false alarm possibility. So this is like a lighthouse, that we're transmitting flashes of energy at different frequencies and at different times. We're communicating information by the location of the energy in time and frequency. And those flashes, however, have to be large enough to be reliably observed and detected. So one of the conclusions of that is that the antenna area for both transmitter and receiver are not reduced by using this scheme. I earlier cited some advantages of minimizing energy per bit. Those advantages all accrued to the reduction in the average power of the transmitted signal rather than the peak power. But in fact, the technique I've described does not reduce the peak power. In fact, it generally increases it a bit, not dramatically, but increases it a bit. And it also does not take any burden off the antennas in terms of collecting that energy. The So it's important to realize that characteristic. The ISM generally narrowly constrains the parameters of time coherence and frequency coherence, so that's good. Tells us a lot about what kind of signal to look for based upon our knowledge of the ISM, which, by the way, is pretty well characterized by astronomers and astrophysicists based on pulsar astronomy. And the observations of pulsar astronomy plus a lot of modeling have told us a lot about this characteristics of the ISM and what these parameters are. One of the nice characteristics of the signal is it's a lot less likely that it will be confused with RFI than other kinds of signals we might look for that are more akin to what we use on Earth, because it looks quite different from typical RFI on Earth. This kind of location coding is not really used in Earth communications, terrestrial communications, for the reasons that I've cited. And obviously, because of the sparseness in time and frequency, we're going to require longer observation times in order to be able to see these isolated bundles of energy. Now, SETI searches have in the past looked for bundles of energy, but whenever there's a bundle of energy which is isolated in time at a certain frequency, then it's generally deemed to be a false alarm, because one of the criteria for distinguishing an interesting signal from false alarms is the persistence of this energy over a period of time. And the kind of signals we're talking about here don't persist in that fashion. So it may in fact be the case, would be really nice if it was the case, that a lot of the false alarms that we've observed in the existing SETI searches are in fact signals of the type that I have described. So how would we discover such a signal? Well, we can do it in a fashion like this. We start by doing a spectral analysis, so we're looking at different frequencies, and then we're looking at the energy within certain short periods of time. This is called a short time Fourier analysis, looking at the energy within certain lengths of time at different frequencies. And whenever we observe an energy that's above some constant times the standard deviation of the noise, which is easy to estimate, we say, well, that's possibly a signal. And in the existing SETI searches, that would be in fact deemed to be a false alarm in most cases. So we take this event and we log into a database the fact that this event occurred, and in that database we store the direction, the time, and the frequency, and we do that possibly for different thresholds on the size of the signal. So later on, when we analyze the database, we have some information about how big the signal was at that time and at that frequency and in that direction. Then we can come back later on. This event database can, I would contend, should be collected for all searches that are done in the SETI sense. This event database is a valuable entity for future analysis in various fashions. So we can go back to this event database, which might be available on the internet or wherever, and apply different kinds of statistical tests for it, looking for signals of the type that I've described. And this is basically a hypothesis testing challenge. The statisticians would call it hypothesis testing, that we're testing the hypothesis that in fact this event database harbors interesting signals which are neither RFI nor signals of natural origin, such as cosmic background radiation. So just a simple start for this kind of analysis. Of course, this statistical testing can get very sophisticated, and the statisticians can teach us a lot about how to deal with that problem. But as a simple start, we might do, for example, a rate analysis. We expect that these events will occur at a certain rate based on cosmic background radiation alone. And when we see a rate significantly higher than that, then that's an indication that something interesting is going on. Another thing we might do is hypothesize that this is a information bearing signal of the type that I've described and encode each of these events in a corresponding binary code and then just do a zip compression of that. Gather this over a period of time and then do a zip compression algorithm on that. And the comparison of the size of this file before and after compression is a measure of the redundancy in this signal. And if for example, if it was due to totally random events due to natural causes, then in general there would be not very much redundancy, and there would be not much compression going on here, or a predictable level of compression going on here. On the other hand, if it's an information bearing signal that has some redundancy in it, then we would start to see a disparity between before and after compression. Anyway, these are really simple techniques that can be programmed in very short order that can get us started, and then over time we can go back and reanalyze this event database using more and more sophisticated statistical hypothesis testing algorithms. So the kinds of signals that would be detected by this kind of analysis that I've just described would include a so-called CW signal, which is a carrier that just persists with time. And generally speaking, SETI searches in the past have oftentimes looked for signals of this type, a continuous carrier, and this would certainly show up in the statistical analysis that I described as being not due to random noise, because it's concentrated at one frequency, whereas random events would be concentrated sort of equally across all frequencies. Another kind of signal would be a periodic set of these energy bundles with spaces in between them. In other words, a single carrier but with a low duty cycle, which I call a lighthouse beacon because it looks a lot like a lighthouse. There's flashes of energy interspersed by nothing. I've shown in the past that for the same discovery probability for these two cases, that with this low duty cycle signal, we can at the same discovery probability, we can reduce the average transmit power by about a factor of 50. So that already has reduced the transmit power by a considerable amount. However, this signal does not communicate any information. These two signals are neither one of them information bearing. They simply are designed to attract attention. But they, however, would be very obvious in the kind of statistical analysis that I just described, looking at the event database, assuming that the observation time was somewhat longer. In the case of the lighthouse beacon, would require a longer observation. Here's a example of a signal that would be easily identifiable. That simply adds a time position element to the lighthouse beacon. That is, it communicates information at no additional cost by simply locating this one bundle of energy at different times depending on what information we're communicating. And that type of signal is called a pulse position modulation, and it's actually used in optical communications for exactly this kind of reason that we've been discussing. In optical communications, they're not concerned about bandwidth, because things like fiber optics have a very wide bandwidth available, and they would like to reduce the amount of energy or energy per bit or average power that they require to transmit the signal. So this pulse position modulation is actually a technique of choice in optical communications, and especially in space optical communications. And of course they add additional bells and whistles to it, but the basic technique is that. And then the kind of technique that I've described, location coding, might look something like this, but we can make it more easily identifiable by introducing redundancy into it. So, and it's kind of up to the transmitter to make their signal easy to identify at the receiver. So, here's a simple technique which, at the expense of doubling the average transmitted power, would make it much more obvious that this was not due to natural causes. By putting energy bundles in pairs at a certain fixed locations relative to one another, and then communicating the information by the location of those pairs of energy bundles. So they've introduced a rather dramatic level of redundancy in the signal to make it easier to identify. Okay, so the point is that using the kind of statistical hypothesis testing that I've described, we can greatly can actually look for a variety of different kinds of signals without being very specific about what signal we're looking for, but rather look for signals which deviate from the case of background radiation alone and are distinguished from that. And of course, we have to deal with RFI, and I haven't discussed RFI. And that's a whole nother talk, a very complicated subject in its own right. But in general, a signal like I've shown up here will be much easier to distinguish from RFI than any of the ones below, because earthbound communication systems generally don't work like this, because there are some conclusions. I'd like to leave you with these following takeaways. First of all, there's a fundamental trade-off between energy and bandwidth in information sharing, and that's always the case no matter what kind of a communication context that we're talking about. But in particular, this trade-off applies to the interstellar communication channel. So there is a fundamental limit on what we can do, and if we're interested in minimizing energy, there's a fundamental limit on the lower limit on the energy per bit that we can achieve, and it's much easier to approach that fundamental limit in the regime where we expand the bandwidth by quite a bit. Techniques get, the larger the bandwidth, the easier it is to approach the fundamental limit, conceptually at least, and that's especially true when we take account of the characteristics of the ISM, and that's especially true if we're looking for simple techniques, which I would argue, due to the lack of coordination between transmitter and receiver, the techniques have to be intrinsically simple. And along with that, by the combination of approaching fundamental limits and avoiding ISM impairments, so that neither the transmitter nor the receiver requires any processing associated with the ISM, and we can approach the fundamental limits because generally any impairments in the ISM that are important will increase the energy required in the transmission. Together, those things provide an implicit coordination between the transmitter and receiver. So I would argue that this implicit form of coordination between transmitter and receiver is actually more important than the reduction in energy per bit or average power required at the transmitter. If you would like more details on what I've just discussed, there's a paper that I published in Acta Astronautica in February of 2015 called Design for Minimum Energy in Interstellar Communication. So I would refer you to that paper for far more detail and quantification of the techniques that I've described here. So with that, that's all I have to offer, and I thank you very much for listening. Bye now.